let's look at the schedule. So homework 3 is due Friday this week. Okay, no more extension. Okay, that's a final deadline. And we're going to start a new tutorial starting from today. And this one will last for 2 weeks. And we won't have a quiz on Monday next week. However, it's going to be Monday after next Monday. So next Monday, we'll have a webinar. I have a guest speaker to talk about IC design and microcontrollers. So he's from the industry, has a lot of patents and products from his company. And please attend it and ask any questions you may have on Monday. It can be pretty useful for you guys. And let's look at the SSDs first, see if there's any questions. If I scroll down, I think I have received a couple of questions from you guys for the decoder. Okay, let's take a look. Do you still remember how to design a decoder just using logic gates from logic? So here's a decoder IC, right? How many inputs? Digital inputs. Is that 4? What are they? A, B, C, D, right? If you have 4 digital inputs, how many possible output patterns you may have? So the maximum amount of output patterns for decoder for 4 binary bits input. 2 to the 4th, right? How many is that? 16. Okay. So these are the truth table for the outputs, right? So A, B, C, D. So these are the inputs. It's manually assign the inputs with a different binary values. So you are getting all these output patterns respectively to light up your self-segment display. Okay, that's how that works. For the very last one, if you want to display a 4-digit number on this 7-segment display, but with 4 digits, right? You need to use a shift register, and we have covered that last week. So all these 4 digits, they are sharing the same data line. You agree with that? If you see all these data lines, they are being shorted to these 7 or 8 digits, okay, including the point, right? But they are also being shorted to the same common cathode. So the way to enable every individual digit is just to give a low to that digit and keep scanning really quickly, so your eye cannot resolve it. So it looks like it's a static number being displayed on this device, but actually it's scanning really quickly. You couldn't see the difference. That's how that works. And I believe most of you have done this. So let's get into the new tutorial for today's experiment. LCDs and sensors. And before we start this one, I just recall one thing. So this is actually a task being assigned in the first tutorial, I guess. Here, Arduino Basics. If you scroll down to the very bottom of the page. So what is this? I believe most of you were in my analog class last semester. So you have taken some of the quizzes regarding the color bands for the resistors. But I want you guys to, rememorize this thing, because you have so many different values of resistor in your Arduino kit. And you do not have a multimeter to test the values of the resistors. So that will be really painful experience if you do not know what are these values. So just memorize all these color bands. And this is an example for the quizzes part of the class taken in analog, right? So you may see a quiz similar to this. I will give you a resistor like that, and you should let me know what's the value, what's the resistance of that resistor. Okay. So the physics behind LCDs is covered by this tutorial, this video, and he did a really good job with animations, and I highly recommend you watch this video after this class. Okay. But for interfacing with the LCD device with your microcontroller, I have a diagram here to show you, and the data sheet for that LCD device can be found here in this link. If you click it, it has a lot of details about the protocol, communication protocol, how to talk to this LCD display. But however, this is a fundamental experiment about LCDs, so we are not going to dive into the details about protocol. So we are going to focus on the applications for this one and make the connections, hardware interface or connections from the Arduino to this LCD, like what I'm showing you here in the figure. And be careful because there's quite a few data lines. If you didn't see anything after you made the connection, check every single line patiently. That's what you want to do. And there's a little potentiometer to adjust the intensity of the backlight of this LCD module. I believe you have one of these potentiometer in your box. If you do not have it, just let me know. I can give you one. So load the library of the LCD display because we are not going to write every single pulse or protocol according to the device. So we need a library to drive it. Load it into your Arduino's library, include the zip file into the folder. So here's example code to give you the first hello world display on the module. So here's on the very top, at the very top, you just include this header file in the folder, and this will define all the pins, all the digital data lines, the parallel data lines from your Arduino microcontroller to the LCD device. And for the setup function, will be executed for how many times? So how many functions do you have in any sketch? Normally, is that 2? So the setup function and the loop function, right? And the setup function will be executed for only once whenever you power up the microcontroller, and the loop function will run forever. It's gonna, after the setup function is done, it's gonna start the loop function and keep going back and forth inside the loop function. So at the very beginning, you need to define the size of the LCD device because your microcontroller doesn't know how many columns, how many rows are there in the LCD device. So you need to tell your microcontroller there are 16 columns and 2 rows of that device. And your print is going to print that string to the display. So in here, set the cursor. So it's going to start displaying anything from, what is 0? What does 0 mean here? So column 0. So the first argument in this function is a column, and start counting from 0, not 1. So 0 means the first column. Okay, the first column and the second row, right? So that's what 0, 1 means over here. So millis is a milliseconds timer. So milliseconds divided by 1,000 will give you seconds, right? So whenever you start running this program, it's going to start counting like a timer from starting from 0, 1, 2, 3. It's like a second timer, right? It's going to display all the seconds in real time on your display module. That's how that works. So the first row is going to show this string on the top, and the second row will show this timer. That's how this works. Okay. So see something like that. And in task 2, there's a little bit more feature will be added to this display. So it's asking you to not just simply use a timer at the second row, but have a, replace that timer using a counter instead. It's counting up to a random number and then being reset to 0. So definitely you need a for loop. So it's always checking the current number right now, and if that satisfies the condition, reset it, then restart from a initial number, which is 0. So I blocked the sketch here, so you probably need to design the script for the for loop. How do you make a counter instead? It should be pretty simple, just a for loop, pretty similar to a MATLAB code. Okay. And the next one is a scrolling text. Let's take a look at this video really quick. So Durango started from the left and stop in the middle of the monitor and blink for a few times, and then start scrolling to the right side of the monitor, and then come back from the left again. So that's what you need to implement to this LCD display. Can you see that? It's hard to see. All right. It's pretty simple. So the way to clear out everything on the LCD display is this function, LCD.clear, parentheses. Because it's a digital system, so it is able to display any digital pattern on the monitor really quickly. So what this one does is actually you write that string, Durango, right, to the monitor to one position, and you are letting your microcontroller keep changing the variable, which is the location, in every loop. So it is able to move the cursor to the right, and once that string reaches the middle of the monitor, that location, stop that scrolling and blink that string on the monitor, right? And then start scrolling the text on the monitor again to the right side of the monitor. All right. Sensors. We have a couple of temperature sensors will be used for this microcontroller. And the first one is this thermistor. Okay. It responds to a temperature variation and changes the resistance of this little device. So there's an equation to calculate the temperature from the resistance change. So here's the equation. It's from the data sheet of the device. So you just need to program this one into your script and get a temperature here. So the unit for this T, the temperature, is in kelvins, and you need to convert it into either Celsius or Fahrenheit. So if you look at the script here, so the line to convert everything, to convert the resistance change to temperature is here. Okay, take a look. If I scroll up, you can see that it's natural log R. So because these two terms has the same factor here, so just factor this out. Natural log R, so you can see it's being taken out to here. Yeah, just use all these parameters. So the constants of A, B, and C, like this one, A, B, C, they are already provided by the datasheet of the manufacturer. So directly plug in everything into the equation here in your script and convert into a temperature you need. So this is a really low-cost temperature sensor. I believe it's cheaper than 10 cents. And it's pretty accurate as well. So where is the hardware connection? Let's take a look. So it's here. Everything else over here, so for the hardware connection, is for the LCD display. So nothing is being changed. So after you get the first connection done in the first section, do not change it anymore. You don't need to unplug everything. So here is just adding a temperature sensor and a 10K resistor to the circuit. And the output is over here. If you look at the circuit here, this is a voltage power supply, goes to one terminal of the thermistor, and then the other terminal, and then the 10K resistor back to the ground. Okay. If this is a resistor, right? This is also a resistor, right? And you are getting a signal from the middle of the two resistors. So what is this circuit? That's a circuit one problem. Voltage divider. Is it a voltage divider? Okay, so when the temperature changes, the resistance here changes as well. So the voltage share being sent to the microcontroller will be changed. So get the data. So here's a quick question, right? Is this data, very simple question, analog data or digital data? Analog data. So you need the input to be where on your microcontroller. So analog signal comes in, right? And you need that one being converted into a digital signal and being displayed on the LCD. So what are the ports can be used to receive this voltage change on your Uno board? If you look at here, you have how many 8 pins? 6 8 pins. What does A mean here? It's analog input. So this microcontroller has embedded analog to digital converter inside and has 6 channels, right? So every single channel can be used to convert analog signal input to a digital signal inside the microcontroller. And you can store that digital signal, digital data, which is in a 1 byte form to a variable, any variable, and then resend it to somewhere else, right? So it has to be an analog input on the board. That's easy to understand. Okay. And you can display the temperature on this LCD. Just use the code I provided in the tutorial. And in 2.1.2, that's another temperature sensor. This is a really versatile temperature sensor because it is able to detect both temperature and humidity, and it's really low cost as well. But let's take a look at the internal structure. Okay, somebody already showed the internal structure here. So this little thing looks really similar to whatever I just introduced to you, right? As a thermistor. So the temperature sensing module in this DHT module is actually a thermistor. And the humidity sensor inside is a special material, something like this. Okay, it has several layers made by salt and some plastic polymer materials. So it responds to moisture changes and converts that change into resistance. Okay? Because all the changes here, including the temperature and humidity, are finally being converted into resistance changes. So it seems like they are analog signals, right? This is a resistance change, which will be a voltage change eventually. So you are thinking maybe I need to do the same thing. It's a voltage change, so I need an analog input on the board and use the ADC to convert it into a digital signal. But however, if you look at the pin out for this sensor, we are using this one. Okay, it's a DHT11, not the DHT12. So look at the pin out of this module. Definitely you have VCC and ground, power 5 volts and ground, and there's the not connect, right? So NC, you just don't need to do anything for this pin, but there's only one data pin from here. If you look at the script I provided on the tutorial, so digital pin 2 on the board or of the 322P microcontroller is being used to be connected to the data pin. Right, pin 2 is for data, being shorted to the data pin of the temperature module. And if you scroll down, so take a look here, there's no sign or no analog read at all. So nothing is doing an analog read. And also pin 2 is not an analog pin. If you look at the pin out of the of this guy, see pin 2 is here, right? It's not being connected to any of the analog pins. So pin 2 is a digital pin, so it's doing a digital reading from pin 2. So the problem is we are thinking like this sensor is doing an analog conversion, or is the output of the sensor should be an analog signal, but eventually the output pin of this module is being shorted to the digital pin on the board. So why is that? Any thoughts? Because the temperature sensor inside the module is a thermistor, which changes the resistance when the temperature changes, right? And it's a voltage divider, so it's going to be a voltage signal output from the module. But however, it's being shorted to the digital pin, so it's not reading any analog signal. So keep in mind, whenever you see a module, everything being encapsulated into something like this, even though you know it's an analog device or analog sensor inside, actually they already have a digital IC chip which converts analog signal into a digital particle for interface with microcontrollers. Even though you didn't see that, but actually it's inside the module. That's more convenient because you only have one pin which can send both temperature and humidity data through one pin. Okay, so let's take a look at this piece of code for this sensor. So first of all, load the library on the top. So it's a simple DHT.h. So I already provided this in the tutorial. Just download it and put it into the folder. Okay, and do the same thing for the LCD display. You don't need to change anything for it. And declare the digital pin being used on the microcontroller for the digital reading, right? And initiate the instance of this module. And there's a setup function, define the size of the LCD display, and then the loop function. So here's the byte type data, right? Do you still remember what is a byte? How many bits in there? 408, 8 bits, right? And in this Arduino architecture or CPU, a byte is signed or unsigned. This is critical. Keep in mind, this is pretty important. That sometimes if you use a byte for a float data type, it won't work at all. So is byte signed or unsigned? You forgot everything? You need a quiz on this? You don't need a quiz on this. Is byte signed or unsigned? All right, so go back to Arduino Basics, that tutorial, the second tutorial, right? And so a byte is unsigned, always positive, right? Keep in mind. And here's a data array. It's a byte array. So there are 40 elements, data points in this array. It has 40 spots, and every spot can hold one single byte. Okay, and this is written in the library, and you don't need to dive into that library. Just use it. So DHT11.read. So this is a method in this class, right? So it's going to be a something dot something object oriented programming, right? If you have learned that, if you haven't, which is fine, just know that the read function is a method for this class, right? DHT11.read, and these are the 4 arguments you want to use for this library. And the first one is going to tell the library where is the data pin, which is pin 2. So because I declared 2 as this one, right? So that's the address of this pin for reading the data from the module. And these are the 2 variables will hold the temperature and humidity data in these 2 variables later on. So this library will do everything for you. You just need to define the pin and define the 2 variables you want the microcontroller to store the data. And the final one is the raw data, binary data for both temperature and humidity at the same time. But this one only holds the temperature data. This one only holds the humidity data. But this is going to have both, but in the binary form, raw data. And print, so you can see the display on the LCD module. So it's going to be something like this for if you run this code in your microcontroller, right? However, if you want to understand what's going on in the raw data, here's an example. Just directly run it, but also you want to demonstrate this and take a picture or record this demonstration as a video and upload to your lab reports online. So if you look at this one, I have a little loop to display the raw data in your serial monitor. If you look at here, so this for loop, so remember the variable data stores what from the sensor? This guy. Let's go back. I think I should have a line somewhere here. Yeah, it's here. So it's here, right? So it declares this byte array in the front. And this function will store what in data in that variable specifically. I just mentioned that, right? Let me just repeat this. So the data variable is going to store the raw binary data of the temperature and the humidity into one variable. So now we are trying to display all this raw data in the binary form in the serial monitor, so you know what's going on or what's being sent from the module to the microcontroller. Okay, so now here's a for loop to do this job. Just do a loop and have an index starting from 0 to 40, so you can scan all the binary data in the array. Okay, and every time you find out that data at that location and print it. Because the digital system can run really quickly, so you can display all the digits in the serial monitor really quickly as one piece of data, right? So what does this mean? This percentage sign. What's this one doing here? You see. Is that I plus 1%? No, what is that? Remainder, right? It's getting a remainder. So whenever this guy divided by 4, the remainder is 0, then you just print a space. So it is actually trying to separate every 4 digits of the data. It looks better on the serial monitor. If you have all these binary numbers in one line, you don't even know what are they, right? They're all stayed together, and there's no gap to separate all these hex numbers. If you have all these binary bits in one line, it's going to be hard to tell what are they. So it's better to separate every 4 binary bits in a line. So finally, if you do this, you are going to see something like here. Boom, 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 4. So every 4 bits is going to print a space after that. And the first 8 bits here is the humidity data. And then it's going to print 8 0 bits. And then the Celsius temperature data. And then another 8 binary bits. And finally, the temperature data, but in Fahrenheit. Okay? That's the raw data from the sensor. And do you think this is an analog device or analog output or digital output from the module? Definitely digital, right? Something has been converted from analog to digital right in the module. So to make it more user-friendly, you don't need to worry about that too much. And by doing this, you can get the humidity data, the temperature data in Celsius, and the temperature data in Fahrenheit in one data stream, and can be sent from the module to the microcontroller just using one line. Do we have multiple data lines from the module? There's just one data line, right? So it's a one-wire communication, which can save a lot of pins on a microcontroller. So that's why this is a really good sensor. It's not super accurate in terms of the humidity sensing, but I think it's pretty good. So when you are demonstrating this, the functionality of your connection, after everything is being set up, right? So you need to record a video demonstration, and just use a brace, just blow the sensor, so you'll see the humidity changes, and you need to record that change in the video and upload the video to the website as a report. Don't forget to do that. So let's take a look at this. The first one. Let's verify it if this is correct. So I display the decimal form just below this raw data, 22 Celsius, right? So can you let me know if this is 22? How can I verify it? From the raw data on the top, is this a 22 Celsius? Is this 22 Celsius? Where is the Celsius data? Here, 1 byte, right? So what does this digit mean in this binary number? Come on. Huh? 2 to the 4th, right? So what is that? 16. So we got 16. And what are these? 5 or 6? So 4 plus 2 is 6, right? So 6 plus 16 is 22. So here's a 22 Celsius degree showing here. And that's a humidity data, 51%. Let's verify it. So this is 16, this is 32. So 32 plus 16 is 48. And 48 plus 3 is 51%. So that's a humidity data. So you want to display the temperature and the humidity at the same time on the LCD module. Okay. Just from this single module can do both. That's a good deal, right? So after that one, there's another temperature sensor I want to I like you guys to try. So the name of the sensor is TMP36. If you do not have it in your box, I have some of them over here. After class, just grab them from here. And which company made this sensor? Let me know. There's some common sense I've been I have telling you guys all these companies you need to know. So Analog Devices, right? So Analog Devices acquired which company a couple of years ago? Linear Technology. So LT, whatever chip, all the ICs starts with LT, blah blah blah. It came from Linear Technology. So LT Spice is designed by Linear Technology, right? And so here's a temperature sensor from Analog Devices, which made a lot of really high-end ADCs, DACs, all these IC chips. Here's one thing you need to know. Definitely do not swap the ground and power, which will heat up this sensor really quickly. I believe some of you guys, if you took my Engineering 104, probably have tested this sensor in the past. If you swap the power line and ground line, the sensor will become super hot. And remember, when you are trying to test the temperature sensor, you need to use your fingers to warm it up, right? So you can demonstrate it. If the sensor becomes super hot, it's going to burn your finger. You'll smell something, okay, like a barbecue finger or something. So definitely check the connection before you power everything up. That's super important. It's going to burn your finger, okay? Check it. So look at the pin out. That's the bottom view. 1, 2, 3. And 1 is power, 5 volts, and 3 is ground, and the middle pin is a V out. So before I get into the data sheet for this sensor, if you just look at V out, now tell me if this is an analog sensor or digital sensor. Is that an analog output or digital output? Analog output. Okay. So you need to connect the middle pin to where? To the A pins. Is that correct? Because the digital read pins cannot read analog signals, right? It only understands 1 and 0s, nothing else in between. So you need to connect the middle pin to any of these ADC inputs. And there is an equation to convert that analog voltage into a temperature. So you can look for that from the data sheet, but I already provided over here. So that's the equation. You have to just use it. So it's going to convert everything into temperature. So you can display it over here. Okay. So when you are demonstrating this and reporting this experiment, keep in mind you need to record a video, right? You cannot just display a static temperature. I don't even know if it's working or not. You need to record a video and warm it up. Use your, probably not fingers if you are afraid of getting burned. Something else, whatever you can demonstrate it, right? And record a video and upload to the website. Okay. And next is a remote sensor. It's also a highly integrated sensor. It's detecting the remote signal, error signal, and convert it into a digital data. So there are only 3 pins for this receiver. VCC is being shorted to 5 volts, and ground is being grounded to the Arduino board. And there's the data pin being directly shorted to a digital pin. So whenever you see a data pin on the module, is that a digital sensor or analog sensor? Is that digital or analog? Digital, because the data is not V out, it's a data pin. Okay, it's being shorted to a digital pin on the board, which is D5. You don't have to use D5, can be any digital pins which can do the digital rating. Any GPLs on the board will work for this purpose. And you may have a remote like this in the box. If you have some of these ones, do not use it. Ask me for another one. If I have a lot of better ones. This one is not working really well. It's giving you a lot of error code to the controller. So here's the receiver, here's the remote controller. You press the pin, the push button on the remote controller, and this receiver will receive it and convert it into a digital signal and being received by the microcontroller. So you have a LCD to display the code for every single button. Whenever you push that push button on the remote controller, there's a specific code for that button only. So the microcontroller knows which one has been pushed. That's how that works. And this one doesn't work really well. If you have one of these ones, just definitely replace it with a better one. So in the example code, I do not have a lookup table for the better one here, right? So, but you need to make up a lookup table by yourself. So whenever, for example, okay, let's look at this. So it's a switch function, and the results dot value is going to store that digital data being received by the D5 pin. And the switch function is going to switch in between all these cases. And whenever the code being received is this one, okay, what is this number? Which number system? Hex. So every single digit here represents how many binary bits? Every hex digit represents how many binary bits? 4. So F equals to 1111, right? So that's a code for every case here, all right? And if this one is detected, you just print power, which means the power button is being pushed on the remote controller. But where can you find this code from the new remote? Because this is based on the old one, the one you probably have in your box. So how do you figure out which button is which code for that remote controller? Because before you want to verify the functionality of the remote controller, you need to get this lookup table done in your sketch, right? So you have to know which code is being used for which button on the remote controller. How do you figure that out? I don't think you have a datasheet for that one. It's only like 50 cents. It's not providing datasheet online. IR infrared, it's invisible range. Yeah. You mean the wavelength? I forgot it. I think it's over 800 nanometers, if I'm correct. But you don't need to worry about that because it's directly, it's been configured already. You just need to use it, push it, and it's gonna decode everything and being received by the receiver. You're not designing a IR emitter, right? It's done by the manufacturers. So IR range, I think it's it's around 800 nanometers in that range. Yeah. So here's example code, okay? And you need to figure out the code behind every single push button, okay? So turn on the serial monitor and make the hardware connection and load this sketch and delete all the redundant things. So whenever you push it, you don't need to know what is that because everything will be stored in this variable. No. Here. Will be stored in here. You don't need to know what is in there, but you just want to print that variable to your serial monitor so you can see that value in your serial monitor. You push it, and you open the serial monitor and you see that value and write it down or probably copy and paste to a spreadsheet until you are done with all the push buttons. So you can type everything in this sketch. Okay. Do you understand that? You know what to do for this one? Great. You may see a decimal number in the serial monitor, but how do you convert it into hex? Manually? It takes 10 years to get everything done, right? How do you want to do that? So every time you press it, you are going to see this number, 167, blah, 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 all these things, right? So that's a decimal number. The serial monitor is only reading, it's going to automatically convert everything to decimal. And if you see that decimal number in serial monitor, and you just open your calculator in your laptop desktop, doesn't matter, just open this programmer or anywhere else can convert that decimal number here into a hex number and use that hex number for the lookup table. Is that clear? Okay, great. And after that, there's a pretty important experiment. I think it's more important than anything else on the from the beginning of this tutorial. So it's a bare-bone microcontroller because everything we have been using is based on the Uno board, and there are so many redundant parts. If you look at the Uno board, you know there's a USB cable, there's a serial USB to serial converter and everything, but definitely you don't need it for a real application. Okay? So what we are going to do here is to convert everything into an independent embedded system. Instead of using everything on the Uno board, you need to lift that microcontroller from the socket on the board carefully. Okay, if you damage it, I'm going to ask you to pay for that. So be careful about the pins; they are pretty fragile. So lift it from the socket and place that microcontroller on a breadboard and make these connections accordingly. So you will need a crystal oscillator, which is a 16 megahertz. I have it here. If you probably you guys don't have it, just pick up one. So you need an oscillator. These ones. So 16 megahertz crystal oscillators and 22 picofarads capacitors. So what you need to do is make this connection to the microcontroller. Just look at the pin out of the 328P microcontroller and make this connection and power it up and ground it. That's all the things you need to do to make it run on the breadboard. It's pretty simple. But however, if you put everything on the breadboard, you probably want to reprogram it. Because every time if you want to program it on the Uno board, you have to take it out from the breadboard and replug into the Uno board, right? And program it and take it out and then place it on the breadboard. It's more likely you'll damage the pins. So place everything on the breadboard and short the reset pin. Just use the wire simply short this pin to the reset pin on the Uno board. Okay, that's the first connection you need to make. So this is recorded. Make sure if you forget how to do it, come back to watch this video. All right. This is just a power indicator. Whenever you power it up, you can see the LED will be lighting up. And another thing you need to connect to the Uno board is a serial port, TXRX. So TXRX is being on the board is being connected to this USB to serial converter. Whenever you are uploading your sketch through the USB, it's going to be converted into a serial communication protocol, UART, or it's just serial or UART, whatever you want to call them. And the code will be, it's sharing the same TX and RX with this pin, these two pins. So if you want to upload your sketch through this Uno board to your microcontroller on the breadboard, you do need to connect TX here to TX on the microcontroller, which is, where's TX? Here. See TX? And connect RX here to RX. Okay? to short it to the board because you already you have taken that out from the socket, right? So you need to reconnect them back to the board in order to program it through the Uno original Uno board. Any questions about that? And make any configurations accordingly to the IDE. So it will work, something like this. So everything is on the breadboard instead of the Uno board, and you program it. So there's another one which is using the interrupt function, and I think I can cover that probably next Wednesday. Sorry. Let's move it here temporarily. So the very last experiment is for interrupt. It's a super important concept, okay? And I'm going to introduce the details and protocol for interrupt next Wednesday, but I will let you know now why do we need interrupt, because whenever, think about the 4-digit 7-segment display. So whenever you are displaying a number over there, it need to be, so the delay between every single digit need to be even. So you can see a very smooth display on the monitor, and you do not want to plug in the temperature sensing code in between the display scanning. So you need to interrupt to test the temperature and then come back to the display. So here's one example. If I don't have the battery here. So that's one of the examples prototype I made a couple of months ago. So what you're going to do is have something like this. That's a 4-digit display module, and you have a bare-bone microcontroller. It's not dependent on any Uno board. I have oscillator and capacitors to create all the clocks. Okay, and this is a 595 shift register, right, to display every single digit over here. And you power it up, use the battery, and it's going to display a temperature over here. So the first 3 digits will be the temperature data, and the very last one can be C or F, Celsius or Fahrenheit. And the temperature sensor I used is a little bit different one, but you can use a thermistor you have in your box. Yeah. So whenever you are sensing a temperature, for example, from a swimming pool, you do not have to update the temperature every single second. Probably just need to update the temperature every like 10 minutes. So you don't have to keep sensing the temperature all the time, which is consuming power. You just put all the temperature sensing code into the ISR, which is interrupt service routine, into the interrupt every 10 minutes. So it just keeps doing the display in the loop all the time. And whenever, after every 10 minutes, you can trigger ISR and do the temperature sensing and then come back. Is that making sense? Okay, so the temperature in the swimming pool is not changing every second, right? You don't need to sense that temperature in real time. So that's one of the applications you need to interrupt for your design. And anyway, we're going to cover that on Wednesday next week. Okay, so there's no more extensions for homework thread. Okay, make sure you upload it by Friday. Okay. See ya.